Hello everyone. Last week we talked about inferences about one population. This week we will extend that to two populations. We're going to talk about inferences about two populations. We're going to begin with population proportions. So today we're going to distinguish between independent and dependent sampling. We will test hypotheses regarding two proportions from independent samples. We will construct and interpret confidence interval for the difference between two population proportions. We will determine the sample size necessary for estimating the difference between two population proportions. A sample method is independent when the individuals selected for one sample do not dictate which individual are to be selected for the second sample. A sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals to be in the second sample. Dependent samples are often referred as matched pairs samples. It is possible for an individual to be matched against him or herself. And let's look at the two examples to see the difference between independent and dependent sampling. A researcher wants to know whether the price of one night stay at a Holiday Inn Express is less than the price of a one night stay at a Red Roof Inn. She randomly selects 8 towns where the location of the hotels is close to each other and determines the price of a one night stay. The other example is a researcher wants to know whether the state quarters introduced in 1999 have a mean weight that is different from the traditional quarters. He randomly selects 18 state quarters and 16 traditional quarters and compares their weights. Notice from the first example that the sampling method is dependent. The 8 Holiday Inn Express hotels can be matched with one of the 8 Red Roof Inn hotels by town, while the second sampling method is independent, since the state quarters which were sampled had no bearing on which traditional quarters were sampled. Let's look at the sampling distribution of the difference between two proportions. We studied before the distribution of sample proportions, and this is similar in that sense. So, a simple random sample of size n1 is taken from a population where x1 of the individuals have a specified characteristic. And a simple random sample of size n2 is independently taken from a different population where x2 of the individuals have a specified characteristics. The sampling distribution of p1 hat minus p2 hat, where p1 hat is equal to x1 divided by n1, and b2 hat is equal to x2 divided by n2, is approximately normal, with a mean of p1 minus p2, that is the population proportion of the first sample minus the population proportion of the second sample, and the standard deviation is given by this formula, which is equal to the square root of p1 times 1 minus p1 divided by n1 plus p2 times 1 minus p2 divided by n2, provided that n1 times p1 hat times 1 minus p1 hat is greater than or equal to 10. And similarly, n2 times p2 hat times 1 minus p2 hat is greater than or equal to 10, and the sample size is no more than 5% of the population size. So now that we have the distribution of the difference between two proportions, we can find the standardized version of p1 hat minus p2 hat, which can be written as z is equal to p1 hat minus p2 hat minus the mean for the distribution of difference between two proportions, which is p1 minus p2, divided by the standard deviation of the sampling distribution of the difference between two proportions, which is the square root of p1 times 1 minus p1 divided by n1 plus p2 times 1 minus p2 divided by n2, which has an approximate standard normal distribution. So we're going to follow the z distribution that has a standard normal distribution, and just like we did when we estimated the population proportion, we're going to find the point estimate. We're going to call this estimate a pooled estimate. The pooled estimate p hat is equal to x1 plus x2 divided by n1 plus n2, and in order to test hypotheses we need to come up with the test statistic. The test statistic z naught is equal to p1 hat minus p2 hat divided by the standard deviation, which can be written as p1 hat minus p2 hat divided by the square root of p hat times 1 minus p hat times the square root of 1 over n1 plus 1 over n2. In order to test the hypotheses regarding two population proportions p1 and p2, we can use the steps that follow, provided that the samples are independently obtained using simple random sampling, and that n1 times p1 hat times 1 minus p1 hat is greater than or equal to 10, and n2 times p2 hat times 1 minus p2 hat is greater than or equal to 10, and the sample size are no more than 5% of the population size. This is required to ensure the independence necessary for a binomial experiment. We're going to estimate the binomial distribution using a normal distribution instead. And the steps in order to test the hypotheses regarding two population proportions from independent samples are as follows. Step 1, we need to determine the null and alternative hypotheses, just like we did when we tested the hypotheses for one population proportion. The hypotheses can be structured in one of the three ways. The first way is when we have a difference and we say we had a two-tailed test, we're going to write the null hypothesis as a statement of equality, and the alternative hypothesis is going to be as a statement of inequality. So here is the first way to write it down, and we know in this case we're going to have a two-tailed test. And we need to find z sub alpha divided by 2 negative z sub alpha divided by 2. And alpha is basically the area in both of these tails, which is also known as the probability of making type 1 error. The second way to construct the hypotheses is to perform a left tail test, which is when we say in the language of our question that we believe that the proportion is now less or has decreased or something indicating these two terms. We're going to write the null hypothesis as a statement of equality, and we're going to write the alternative hypothesis as a statement of inequality using less than. We know that P1 is the population proportion for population number 1, and P2 is the population proportion for population number 2. The last way to write the hypotheses is to perform a right-tailed test. That is, we're going to state the null hypothesis as a statement of equality and the null hypothesis as a statement of inequality, and we're going to use greater than. So for this case, we have a left-tailed test, and for this case, we're going to have a right-tailed test. This is alpha, and this is z sub alpha, and this is alpha, and this is negative z sub alpha. So now we know, and we notice the similarities between what we have done before and what we're doing right now. The only differences are going to be the formula that we compute z naught with is going to be different for the two populations. And the next step is going to be selecting the significance level. Sometimes you will be given a confidence level. That's where you're going to select your confidence significance level from. We know that the significance level alpha is equal to 1 minus the confidence level. And we know that alpha is going to depend on the seriousness of making type 1 error. The third step is to compute z naught. From the previous approach for one population, we computed z naught differently. We said that z naught is equal to p hat minus p divided by the square root of p times 1 minus p divided by n. In this case, we have two populations. So we're going to find z naught differently using this formula over here. We're going to say it's p1 hat minus p2 hat divided by the standard deviation for the difference between two population proportions, which is this one over here. P hat is the pooled estimate, and it's equal to x1 plus x2 divided by n1 plus n2. So this is how we're going to compute P hat, which is this value over here. N1 is the size of the first sample, and N2 is the size of the second sample. P1 hat is point estimate for the first population, and P2 hat is the point estimate for the second population, which is equal to x1 divided by n1 and x2 divided by n2. The fourth step is to determine the critical values. When we use two-tailed test, we're going to determine z sub alpha divided by 2, and we know that we have two of them. One is positive and the other one is negative. So to compute positive and negative z sub alpha, it's positive and negative norm dot s dot inverse of 1 minus alpha divided by 2. And then the right-tailed test, we're going to find the critical value as follows. It's z sub alpha is equal to the norm dot s dot inverse of 1 minus alpha. So here, for the two-tailed test, we're going to have z sub alpha divided by 2, and we know that there is another one that is negative. For the right-tailed test, we're going to compute z sub alpha. And for the left-tailed test, we know we're going to compute z sub alpha, and it's going to be negative. So we're going to compute it this way. So now that we know the critical value and we know z naught, we can use the classical approach in order to make a decision. We know that for the two-tailed test, here is our critical region, which is colored blue. So if z naught that we computed happens to be greater than z sub alpha divided by 2, or it is less than negative z sub alpha divided by 2, we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis if z naught happens to be between those two values. Similar for a left-tailed test. So if the computed z naught is less than negative z sub alpha, then we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. And if we have a right-tailed test, then if z naught is greater than z sub alpha, then we're going to reject the null hypothesis. Otherwise, we're going to fail to reject the null hypothesis. Again, we're going to use different z naught, and this is the difference between the one population proportion and two population proportion hypothesis tests. So the only difference is not the concept itself, it is finding z naught. When you find z naught, it has a different approach of finding it, which is represented with this formula. That's what we call the classical approach. There is another approach that we know, which is the p-value approach. So in the p-value approach, you still need to find z naught. After you find z naught, then you're going to see how you're going to determine the p-value. The p-value is going to be determined based on the type of test you're performing. So if it's a two-tailed test, the p-value is going to be 2 times 1 minus norm dot distribution of z naught, comma true. This is basically 2 times the area to the left of z naught or to the right of z naught if it's positive. And we know how to find that. So what I did here, I computed the area to the right of z naught and multiplied that by 2 because I know in the two tails I will have 2 areas. So I computed this area over here and I multiplied it by 2. So this is half of the p-value in the two-tailed test. If we have a right-tailed test, then the p-value is going to be the area to the right of z naught. This area right here, that's going to be the p-value. And we know how to compute that using Excel. And I gave you the formula right here. If we have a left-tailed test, then the p-value is going to be the area to the left of negative z naught. And I gave you the value. I gave you the formula to compute that on Excel. So that's how we're going to compute it on Excel. Now, this is an illustration of the p-value and how we're going to find the p-value, which is the probability of z greater than z naught in the case of two-tailed test, and it is the probability of z less than z naught in case of left-tailed test, and it is the probability of z greater than z naught if we're talking about a right-tailed test. Again, we're going to use Excel to compute the p-values, and I showed you the formulas in order to compute this, the p-values. This is the classical approach. After we find z naught and z critical, we're going to compare them, and I showed you when we're going to reject the null hypothesis and when we're going to fail to reject the null hypothesis for all of these tests: the two-tailed test, the left-tailed test, and the right-tailed test. For the p-value approach, if p-value is less than alpha, we will reject the null hypothesis. If p-value isn't less than alpha, then we're going to fail to reject the null hypothesis. And eventually, we're going to state our conclusion. Our conclusion is going to be basically either we're going to have evidence to support our alternative hypothesis or our claim. In this case, we're going to reject the null hypothesis. Or we don't have enough evidence based on the information we collected, and we can't reject the null hypothesis, so we're going to fail to reject the null hypothesis. Let's look at some examples and see how we're going to compute the examples. An economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. Let's begin with writing our hypotheses. So, the null hypothesis is a statement of equality. So I'm going to say P1 is equal to some value. And then I'm going to say the alternative hypothesis is P1 is greater than P2. The proportion from the first one is greater than the proportion from the second one. Let's read the rest of the question and determine what we have here. He obtains a random sample of 800 urban households and finds that 338 of them have internet access. So x1 is equal to, or n1, let's begin with n1. So the size of the first sample of the population is 800 and x1 is equal to 338. And then n2 is equal to 750 and x2 is equal to 292. Test the economist claim at alpha is equal to 5% level of significance. So alpha is equal to 0.05. We have our hypotheses written and we have everything we need. Let's go to the computation part. So here are the numbers again. From these numbers we can find P1 hat, which is x1 divided by n1. That will give us this number. And we can find P2 hat the same way, which is x2 divided by n2, and we're going to come up with this number. Next, we're going to test for or ensure that the independency condition is met. That is, we're going to use the first formula, n1 times P1 hat times 1 minus P1 hat, which is equal to 195, definitely greater than 10. So this is met, and we're going to repeat for the second sample as well. The sample sizes are less than 5% of the population size. We want to determine whether the percentage of urban households with internet access is greater than the percentage of the rural households with internet access. So here is our hypotheses. We written them again, which is equivalent to, we can say that the null hypothesis is P1 minus P2 is equal to 0, and similarly we can say H1 is P1 minus P2 is greater than 0. We know that the significance level alpha is 5%, so we're going to proceed. The next step is to find the pooled estimate. The pooled estimate equal to x1 plus x2 divided by n1 plus n2. The p hat is going to be equal to this number. Next, we're going to find the statistic. We know that z naught, it's equal to p1 hat minus p2 hat divided by the square root of p hat, which is we computed in this step, times 1 minus p hat, times the square root of 1 divided by n1 plus 1 divided by n2. Oh, this is the square root of, let me just erase it, let me rewrite it again. So times the square root of 1 divided by n1 plus 1 divided by n2. After we compute z naught, we're going to end up with 1.33 for the z statistic. Now we're going to have to compute the critical value. Since this test is a right-tailed test, then we're going to use we know that alpha is equal to 0.05, so we want to find z sub alpha. Z sub alpha is equal to, which is this area right here, it's equal to norm dot s dot inverse of 1 minus alpha, which is this area to the left of it, to find this point right here. So if you do that using Excel, you're going to end up with z alpha is equal to 1.645. Now, after you computed z alpha, you're going to compare it to z naught. Z naught is 1.33. So here is z naught, which is 1.33, and z sub alpha is greater than that. Z sub alpha is greater than that, which is the z critical. So here is my critical region right here, and I notice that z naught is outside of that critical region. As a result, we're going to fail to reject the null hypothesis because z naught is outside of the critical region. If it was inside the critical region, then we have to reject the null hypothesis. The interpretation is, in this case, we don't have enough evidence that our alternative claim is valid, so we're going to fail to reject the null hypothesis. Meaning, we don't have evidence to support the claim that says the percentage of urban households with internet access is greater than the percentage of rural households with internet access. So we're going to fail to reject the null hypothesis in this case. Let's see how we're going to use the p-value approach in order to reach the same conclusion. After the step that you find z0 is equal to 1.33, you're going to compare z0. You're going to find, since this is a right-tail test, we're going to find the area to the right of z0, which is equal to norm dot s dot distribution, or 1 minus norm dot s dot distribution of z0 comma true. In this case, you're going to end up with the p-value is equal to 0.09. We know that alpha is equal to 0.05. So notice how p-value is not less than alpha. It's not less than alpha. The p-value isn't less than alpha. In other words, p-value is greater than alpha. Since p-value is not less than alpha, we're going to fail to reject the null hypothesis. We only reject the null hypothesis if p-value is less than alpha. So the conclusion for this test is we say that there is not enough evidence, or there is insufficient evidence that at alpha is equal to 5% level of significance to conclude that the percentage of urban households with internet access is greater than the percentage of rural households with internet access.